Hi, my name is Luca, and along with my project team members, Yosef, Aslam, and Kevin, we explored event sequence modeling for ICU patient mortality prediction. We want to predict mortality in the ICU so that we can detect clinical problems early to improve the probability of saving a patient's life, the allocation of ICU resources, physicians' decision-making capabilities, and risk stratification. Our goal was to produce a predictive model that generates the highest AUC. For this, we explored LSTM, GRU, and CRF. We used the MIMIC3 database containing de-identified data on roughly 40,000 ICU patients. We extracted features from the patients and chart events tables. Our original dataset contained 34% deceased patients and 66% alive patients. After applying an observation window, we were left with 22% deceased patients and 78% alive patients. We extracted the following columns and applied min-max normalization on the values. We then grouped the data into 1-hour windows and computed mean value for each item using each item ID as a unique feature. We also applied an observation window of 180 days prior to the index date. The index date for a deceased patient was the date of death minus 1 day, and the index date for an alive patient was the timestamp of the last chart event. For data preprocessing, we used Apache Spark cluster in AWS. The preprocessing code was written in PySpark. For training and prediction, we used 2 machines, both with 16 gigabytes of RAM and i7 CPUs. We leveraged PyTorch as the model training framework. The GRU variation of RNN consisted of a fully connected first layer with 32 hidden units, a GRU layer with 16 hidden units, and an output fully connected layer with 2 output units. A TAN activation function was applied after the embedding layer. The LSTM variation follows the same architecture, but the GRU layer is replaced with an LSTM layer. CRF is a probabilistic framework for labeling and segmenting structured data such as sequences. Usually, CRF is used to predict subsequences, but we adapted it to predict mortality. We trained the CRF with gradient descent using the LBFGS method, using default values for C1 equal to 0 and C2 equal to 1. We used decision trees for feature selection. The tree was trained with a max of 50 nodes, and importance score for each feature was extracted from the model. We selected all the features with importance value greater than the mean of all importance values, reducing features from 2,462 to 320. For all features, the LSTM model labeled alive patients as alive 90% of the time and deceased patients as deceased 61% of the time. For top features, the model labeled alive patients as alive 97% of the time and deceased patients as deceased 43% of the time. For all features, the GRU model labeled an alive patient as alive 96% of the time and a deceased patient as deceased 50% of the time. For top features, the model labeled an alive patient as alive 97% of the time and a deceased patient as deceased 42% of the time. The CRF model required additional pre-processing prior to training. Training data was used to train the CRF, while the valid data set was used for evaluation to produce AUC, precision, and recall. The normalized confusion matrix and ROC curve are displayed here. The LSTM model produced the highest AUC with 0.756. Overall, the results were disappointing for predicting mortality. The best model correctly predicted mortality only 61% of the time. Using decision trees to select top features did not improve the results, which may indicate that the model is able to handle noise or that the feature selection technique was selecting features that did not capture all use cases. Although CRF's ability to detect patterns in sequences of data seemed like a promising approach, the results were disappointing, which is not entirely surprising considering that CRF was not designed to solve a prediction problem. To achieve better results, we would explore additional datasets, implement feature cleaning to standardize units of measurement, utilize cohort selection and segmentation through unsupervised learning techniques such as clustering or rule-based mechanisms, explore natural language processing on free text notes, and try other model architectures with a combination of standard dimensionality reduction techniques such as PCA. This concludes the presentation. Thank you for watching.